There is light in a place we were certain was dark. Not dim, not hidden, not theoretical. Light blazing across 13 billion years from an era we had labelled the cosmic blackout, a time before stars were supposed to exist, before galaxies were meant to ignite, before the universe had switched the lights on. And yet, when the James Webb Space Telescope opened its gold-plated eye and stared deeper than any machine in human history, it found brightness where silence was expected. We thought we understood the beginning. We were wrong. For most of human history, night meant absence. You step outside, the sky is black, stars puncture it like pinholes in fabric, but between those stars, darkness. It feels infinite, calm, empty. The early universe was supposed to be like that, but worse. After the Big Bang, the cosmos was a furnace. Particles collided violently. Light existed, but it was trapped inside a dense fog of charged plasma. Then, about 380,000 years after the beginning, the universe cooled just enough for atoms to form. Hydrogen, helium, simple, quiet. Light finally escaped. And then darkness. No stars yet, no galaxies, just vast oceans of neutral hydrogen stretching across expanding space. Gravity was working, yes, pulling matter into denser regions, but nothing had ignited, no nuclear fire, no fusion. Astronomers called it the cosmic dark ages. For hundreds of millions of years, the universe was supposed to be starless. Imagine that scale. If the entire 13.8 billion year history of the universe were compressed into a single year, those dark ages would stretch across weeks of total night. No sunrise, no flicker, just cooling gas and the slow patience of gravity. We believe the first stars, the first true sources of light, formed perhaps 200 to 400 million years after the Big Bang. Massive, short-lived giants that burned hot and died violently, seeding the cosmos with heavier elements. That timeline was neat, predictable, clean. And then Webb looked further. Webb does not see like we do. It's mirrors, coated in gold. Gather infrared light, the stretched, reddened glow of ancient objects whose wavelengths have been pulled long by the expansion of space itself. The farther something is, the faster it is moving away from us. The faster it moves away, the more its light stretches toward red. At extreme distances, visible light becomes infrared. So to see the first light, we had to look in the infrared. And when Webb stared into regions that had already been photographed for weeks by Hubble patches of sky so small they could be covered by a grain of sand held at arm's length, it found something astonishing. Galaxies, not faint hints, not barely their smudges. Galaxies that appear massive, structured, luminous, existing just 300 million years after the Big Bang. Some candidates may be even earlier. This is not a subtle shift in schedule. This is like arriving at a construction site expecting to find empty land and discovering skyscrapers already standing. We expected cosmic dawn to flicker slowly. Instead, it may have exploded. To understand why this is unsettling, we have to feel the physics. Gravity begins as a whisper. After the Big Bang, matter wasn't evenly distributed. Tiny fluctuations 1 part in 100,000 meant some regions were slightly denser than others. Over time, gravity amplified those differences. Dense regions pulled in more matter, clouds formed, gas compressed. But compression takes time, cooling takes time, collapse takes time. We calculated that time. And now, the light suggests something moved faster. Some of the early galaxies Webb has observed appear surprisingly bright. Brightness implies stars, many stars, massive stars, enough to assemble large stellar populations in a cosmic heartbeat. A few 100 million years. That might sound long until you remember the universe is 13.8 billion years old. This happened in its infancy, its first 2% of life. Imagine a newborn building a city before it learns to crawl. We are not talking about a single star igniting. We are talking about entire galactic systems forming, organizing, and shining across hundreds of thousands of light years. And that light has travelled to us. Every photon that Webb captures left its source when Earth did not exist, when the Sun was not yet born, when our galaxy, the Milky Way, was still assembling itself. That light crossed expanding space for over 13 billion years, dodging dust, slipping between galaxies, stretching longer and redder until it struck a mirror floating 1.5 million kilometers from Earth. And now we are looking at it. We are seeing into an era we thought was completely dark. Which means one of two things. Either galaxies formed much earlier and faster than our models predicted, or something about our understanding of the early universe is incomplete. Notice what this does to us. For decades, we built simulations of cosmic evolution. We tuned them carefully. We fed in dark matter distributions, cosmic inflation parameters, baryon densities. The models reproduced the large-scale structure of the universe beautifully. Filaments, voids, clusters. It felt solid. But the earliest moments after darkness lift that transition from simple hydrogen fog to blazing galaxies may not have unfolded the way we imagined. Perhaps the first stars were far more massive than expected, hundreds of times the mass of our Sun, burning intensely and collapsing quickly, accelerating structure formation. Perhaps dark matter behaved differently at small scales, clumping more efficiently. Perhaps cooling mechanisms allowed gas to collapse faster. Or perhaps the universe simply had more urgency in its youth. Whatever the explanation, Webb's data has done something profound. It has shifted the emotional map of cosmic history. The Dark Ages may not have been so dark. Picture standing on ancient Earth, long before humans, long before complex life, staring at the night sky. Even then, those first galaxies were already billions of years old. Their ancient light was already travelling. Our entire evolutionary story, fish crawling onto land, dinosaurs rising and falling, mammals emerging, primates standing upright, unfolded while that light was still in transit. We are latecomers to a very old glow. And yet, in a strange way, we are perfectly timed. Because only now do we have the tools to see it. The James Webb Space Telescope is not just observing distant objects, it is collapsing distance in time. It is allowing us to witness the moment the universe began to turn luminous. And what it is showing us is not a timid dawn. It is a blaze. If those galaxies are real, and the evidence is mounting that many of them are, then the universe wasted no time becoming complicated. Complexity arrived almost immediately. Think about what a galaxy requires. Not just stars, not just light. A galaxy is gravity sculpted into structure. It is billions of stars bound together, orbiting a shared centre. It contains dark matter halos massive enough to anchor them, gas clouds that cool, collapse, ignite, supernovae that explode, enrich, and trigger more formation, black holes that form in stellar deaths and begin growing at the core. This is orchestration. And Webb is finding signs of it shockingly early. Some of the galaxies detected appear not only bright but surprisingly mature. Their light suggests significant stellar mass, hundreds of millions, possibly even billions, of solar masses assembled when the universe was only a few 100 million years old. That is the cosmic equivalent of a child building a cathedral before learning language. To feel how radical that is, shrink yourself. Imagine floating in the early universe 200 million years after the Big Bang. There is no Earth beneath you, no Milky Way arching overhead. The background radiation is warmer than today. Space itself is smaller. Galaxies are closer together, though none are yet fully grown. In the standard picture, you would drift through vast hydrogen fog, waiting for gravity to patiently gather matter into the first stars. But what Webb suggests is different. Instead of long stretches of emptiness, you might see islands of violent brilliance igniting almost simultaneously. Giant stars forming in clusters, radiation blasting through surrounding gas, regions of space lighting up like scattered beacons. The Dark Ages would not have ended with a single sunrise. They would have ended with a storm of light. This period has a name: reionization. When the first stars ignited, their ultraviolet radiation ripped electrons off neutral hydrogen atoms, ionizing the surrounding gas. This changed the state of the universe. The fog began to clear. Light travelled more freely. Transparency returned on a grand scale. For years, we believed reionization unfolded gradually over hundreds of millions of years, beginning around 400 million years after the Big Bang and completing by about 1 billion years. But if galaxies formed earlier and faster, reionization may have begun sooner and progressed more violently than we thought. The universe may have transitioned from darkness to transparency in a cosmic rush. And here's the deeper tension. In cosmology, timing is everything. The age of the universe is tightly constrained. The density of matter, dark energy, all measured with extraordinary precision. The cosmic microwave background gives us a snapshot of the universe at 380,000 years old, with fluctuations mapped to 5 decimal places. From that snapshot, we run the clock forward. Structure grows, galaxies form, clusters merge. If galaxies appear too early, the clock feels strained. Not broken, but stretched. Because assembling a billion solar masses of stars requires enormous reservoirs of gas. It requires efficient cooling. It requires dark matter halos collapsing rapidly. It requires star formation rates that push against theoretical limits. Some of Webb's early candidates, though still being confirmed, hint at star formation happening at speeds near the physical maximum allowed by gravity. That means the early universe was not hesitant. It was aggressive. Consider our own Sun. It formed 4.6 billion years ago from a molecular cloud enriched by generations of previous stars. Heavy elements, carbon, oxygen, iron were already present because earlier stars had lived and died. But in those first galaxies, there were no heavy elements, only primordial hydrogen and helium. That changes everything. Without heavier elements to help gas cool efficiently, star formation should have been harder. Hot gas resists collapse. Cooling is essential for fragmentation into stars. Yet somehow, stars formed anyway. The first generation, called Population 3 stars, were likely enormous, perhaps 100 to 300 times the mass of the Sun. With no metals to regulate their growth, they may have ballooned to extraordinary sizes. And massive stars live fast and die young. A star 200 times the Sun's mass burns through its nuclear fuel in just a few million years. It explodes in a titanic supernova, forging heavier elements and scattering them into surrounding space. That enrichment enables the next generation of stars to form more easily. So the process can cascade. Massive stars form, they explode, they enrich, more stars form, galaxies brighten. What Webb may be witnessing is the cascade unfolding far earlier than expected. And inside some of those early galaxies, another phenomenon may have ignited just as quickly. Black holes. When massive stars collapse, they can leave behind black holes. If enough mass gathers rapidly in a galaxy's center, a supermassive black hole can begin forming astonishingly early. We have already observed quasars' luminous black holes consuming matter less than 1 billion years after the Big Bang. Even those strained our models. Growing a 1 billion solar mass black hole in under 1 billion years requires sustained, near-limitless feeding. But if galaxies were assembling sooner, the seeds of those black holes may have started growing earlier too. Which means the first cosmic cities may have been built around gravitational monsters from the very beginning. Pause and feel the human scale. We are biological organisms on a rocky planet orbiting an average star in a spiral galaxy 100,000 light-years across. That galaxy contains 100 to 400 billion stars. It formed over billions of years through mergers and accretion. We thought that was the normal pace of things. Webb is showing us that in the universe's youth, growth may have been ferocious. Galaxies may have erupted into existence like cosmic wildfires, and every one of those early systems is unimaginably distant. When we observe a galaxy at redshift 10, meaning its light has been stretched by a factor of 11, we are seeing it as it was more than 13.3 billion years ago. The universe then was roughly 3% of its current age, and yet the structures appear substantial. Not embryonic flickers. Substantial. It forces a subtle but powerful shift in perspective. We often imagine the early universe as simple, clean, primitive. But simplicity may have lasted only briefly. The moment gravity had even the slightest opportunity, it sculpted complexity. Light emerged not cautiously, but explosively. And we are only at the beginning of Webb's observations. Each deep field peers into a tiny fraction of the sky. There are billions of such patches, if even a fraction contain early galaxies as bright as those already detected. The census of the infant universe will expand dramatically, which means this story is not stabilizing. It is accelerating. There is something almost unsettling about how small the window is. Between the moment the universe became transparent when atoms first formed, and light could finally travel freely in the moment galaxies were blazing across space, there may have been only a few 100 million years. Cosmically, that is a breath. To feel that compression, imagine the universe as a single human lifetime of 80 years. The Big Bang is birth. The cosmic microwave background, that first release of light, happens within the first day. For weeks after, nothing shines. Gravity is quietly working in the background. Then, before the infant has even taken its first step, entire cities ignite. That is what Webb is implying, and the implications ripple outward. Because if galaxies formed that early, they were forming inside dark matter halos that must have collapsed extremely fast. Dark matter is invisible, it does not emit, absorb, or reflect light, but it outweighs normal matter by a factor of 5. It is the scaffolding of the cosmos. Without dark matter, galaxies would not exist. After the Big Bang, dark matter began clumping first. It does not interact with radiation the way normal matter does, so it started collapsing under gravity while the universe was still hot and dense. Normal matter, hydrogen and helium gas eventually fell into those dark matter wells. If we are seeing large galaxies at 300 million years, then those wells must have formed even earlier. Which means the invisible architecture of the universe may have assembled with astonishing speed. This is where the tension sharpens. Our best simulations, massive computational universes run inside supercomputers, attempt to recreate this process. They begin with the initial conditions measured in the cosmic microwave background, and evolve billions of particles forward in time. These simulations successfully reproduce today's cosmic web, the vast filaments of galaxies stretching hundreds of millions of light years, separated by immense voids. But zoom into the first few 100 million years, and the details matter intensely. Slight differences in density growth can determine when the first stars ignite. If Webb is correct, something in those early calculations may need refinement. Not revolution, not collapse. Refinement. Perhaps star formation in pristine gas was more efficient than predicted. Perhaps turbulence inside collapsing clouds triggered faster fragmentation. Perhaps radiation feedback behaved differently in the earliest environments. Or perhaps there were simply more dense regions than we anticipated, slight statistical fluctuations amplified by gravity into early overachievers. And here is the part that pulls us closer. Those early galaxies were not calm. The first stars were likely colossal hot, blue-white giants radiating ultraviolet energy that would sterilize any nearby environment. Their surfaces would have burned at tens of thousands of degrees. Their cores would have fused hydrogen at rates unimaginable compared to our Sun. Our Sun has been burning steadily for 4.6 billion years and will continue for another 5 billion. A 200 solar mass star lives maybe 2 million years. It detonates in a hypernova so violent that for a brief moment it can outshine its entire host galaxy. In those first galaxies, Such explosions would not have been rare events separated by eons. They would have been constant. The infant universe may have been a fireworks display. Radiation carving cavities into hydrogen fog, shock waves triggering new collapses, black holes forming and swallowing matter, releasing jets of energy stretching across space. And all of this happening when the universe was only a few % of its current age. Now consider what that means for us. Every atom in your body heavier than hydrogen carbon in your cells, oxygen in your lungs, iron in your blood was forged inside stars. Many were forged inside supernovae. The very first generation of stars created the first heavy elements. Without them, no planets, no chemistry, no biology. If those first stars formed earlier than expected, then the chemical enrichment of the universe began sooner, which means the raw ingredients for life began spreading earlier. Not life itself that requires stable environments and billions of years of calm, but the possibility. In a strange way, Webb is pushing the origin of complexity backward. The universe may have begun experimenting with structure almost immediately. There is another layer to this discovery that is easy to miss but impossible to ignore once you see it. Distance is time. When we observe a galaxy 13.4 billion light-years away, we are not seeing it as it is now. We are seeing it as it was 13.4 billion years ago. That galaxy, if it still exists, has aged alongside us. It has merged, evolved, possibly transformed beyond recognition. But the image we see is frozen youth. We are archaeologists of light, and Webb's sensitivity allows it to detect objects whose photons have been stretched so severely by cosmic expansion that they are invisible to our eyes. Take a photon emitted in ultraviolet light from a young star 13.5 billion years ago. As it travels, space itself expands. Its wavelength stretches. Ultraviolet becomes visible. Visible becomes infrared. By the time it reaches Webb's mirror, it may be 10 times longer than when it left. Webb is tuned precisely for that stretched glow. Its 6.5-meter mirror collects faint infrared signals with a sensitivity orders of magnitude beyond previous telescopes. That is why this discovery is happening now. Not because the light just arrived, it has been arriving continuously for billions of years, but because we finally built an instrument capable of catching it. Think about that alignment. For most of human existence, we had no idea these early galaxies existed. Even a century ago, we did not know other galaxies existed at all. The Milky Way was thought to be the entire universe. Now, within a single lifetime, we are peering back to within a few 100 million years of the beginning. And instead of darkness, we see structure. Instead of emptiness, we see organization. Instead of delay, we see urgency. But the story is not yet stable. Some of Webb's earliest galaxy candidates are so bright that astronomers initially questioned whether they were misinterpreting the data. Could gravitational lensing, where massive foreground galaxies bend and magnify background light, be amplifying them? Could redshift estimates be slightly off? Spectroscopic confirmations are underway. Some candidates have already been verified at extreme redshifts. Others may shift slightly closer in time. But even conservative revisions still place substantial galaxies earlier than anticipated. The trend remains: the dawn is earlier, the darkness is thinner, and that changes how we feel about the universe's beginning. Because we often imagine origins as fragile. The data is suggesting they were explosive. There is a quiet assumption buried inside most of us that beginnings are slow. A seed waits. A child grows gradually. Civilizations take millennia to rise. We project that rhythm onto the universe itself, imagining its first light as hesitant, flickering cautiously into existence. But what if the cosmos did not hesitate? What if the moment gravity had permission, it accelerated toward brilliance with almost reckless speed? James Webb is nudging us toward that possibility. To grasp how radical this is, step into the scale of emptiness that preceded it. After the cosmic microwave background faded into transparency, the universe entered a long, cooling stretch. Hydrogen atoms drifted through expanding space. Temperatures dropped from thousands of degrees to mere tens. Density thinned as space stretched. There were no stars to warm anything, no galaxies to structure the void, just an expanding ocean of gas, smooth except for tiny fluctuations inherited from quantum ripples at the beginning. Those ripples were microscopic differences, one region just slightly denser than another, but gravity does not ignore slight. Gravity amplifies slight. Denser regions pulled harder. They gathered more matter. That made them denser still. Over millions of years, those ripples became wells. Wells became halos. Halos became the gravitational cradles of the first stars. And here is where the pace becomes startling. In computer simulations, this collapse is patient. Gas must cool to fall inward. Pressure resists gravity. Radiation from early stars can heat surrounding gas and slow further formation. Feedback mechanisms regulate growth. It is a delicate balancing act. Yet Webb's early galaxies appear luminous enough to imply that regulation may not have slowed them much at all. Some of these systems may be producing stars at rates tens of times higher than galaxies of similar mass today. That is extraordinary, because today's galaxies already contain heavy elements that make star formation easier. The early universe had none. It was working with raw hydrogen and helium, the simplest elements imaginable. So how do you ignite something complex from something so simple, so quickly? One possibility is that the first stars formed in extremely dense knots where cooling happened faster than expected. Molecular hydrogen, even in small amounts, can radiate away heat. Under the right conditions, collapse accelerates. Another possibility is that dark matter halos formed earlier and were more massive than our average models suggest. In a universe with billions of regions, some will inevitably form ahead of schedule. Webb may be catching the overachievers. But even statistical overachievers have limits. Because time in the early universe was not just short, it was compressed by expansion. When we talk about 300 million years after the Big Bang, we're talking about a universe whose diameter was far smaller than today. Galaxies were closer, matter was denser, interactions were more frequent. The entire cosmic stage was tighter. That density may have fueled rapid mergers, small proto-galaxies colliding, combining, feeding central starbursts, growth through collision rather than calm accumulation. Picture sparks thrown into dry brush. Once ignition begins, it does not stay isolated. Now widen the frame. These early galaxies are not just distant dots. They are signals from a boundary in time we thought we understood. Before Webb, the Hubble Space Telescope had already pushed deep into cosmic history. Hubble's ultra-deep field revealed thousands of galaxies in a patch of sky smaller than a fingernail held at arm's length. Some of them were seen less than 1 billion years after the Big Bang. But Hubble operated primarily in visible and near-infrared light. Its mirror, though powerful, was smaller. Its sensitivity had limits. Webb's mirror is more than twice as wide. Its instruments are optimized for infrared. It can detect light that has been stretched far beyond Hubble's reach. And so Webb stepped past Hubble's horizon. It crossed a threshold. When the first deep-field images came down, astronomers immediately noticed objects with extreme redshifts. Their light stretched so dramatically that it implied extraordinary distance. Some initial estimates suggested redshifts of 12-13, even possibly higher. That corresponds to a universe just 300 million years old or younger. At those redshifts, the universe is less than 3% of its current age. And yet these objects are not faint whispers. They are distinct, structured, bright enough to demand explanation. This is where we must feel the human dimension. Every telescope ever built is an act of defiance against distance. We are a species bound to a planet, wrapped in atmosphere, limited by biology, and yet we've constructed a machine that sits 1 million miles away, shielded from sunlight by a 5-layer sun shield the size of a tennis court, cooled to temperatures colder than deep space, aligned with nanometer precision, all to catch ancient photons. Those photons began their journey before our galaxy finished assembling its spiral arms, before Earth condensed from dust, before the sun ignited, before life emerged. For 13 billion years, they travelled uninterrupted. No guidance, no correction, just straight lines through expanding space-time. And now, they end in a gold mirror engineered by human hands. There is something almost unbearable about that connection. The early universe did not know we would exist. It did not shine for us. Yet here we are intercepting its first light. And what that light is telling us is not that the universe was timid. It is telling us that it was eager. The cosmic dark ages may not have been a prolonged blackout. They may have been the pause before a sudden blaze. And if that blaze began earlier than expected, then our narrative of cosmic evolution shifts subtly but profoundly. The universe did not slowly wake up. It erupted into awareness. Not consciousness, but structure, energy, complexity. And we are beginning to see that eruption not as theory, not as simulation, but as image. A glow from the edge of time, insisting that darkness was never as complete as we imagined. There is a temptation, when faced with something this distant, to detach. 13 billion years feels abstract. 300 million years after the Big Bang feels like a statistic. Redshift. 12 sounds technical, clinical, remote. But this is not remote. This is the earliest chapter of the story that eventually becomes you. Because when those first galaxies ignited, they changed the universe permanently. Before starlight, the cosmos was chemically simple hydrogen and helium, with traces of lithium. That was it. No carbon chains, no oxygen to bind with hydrogen into water, no silicon for rocks, no iron for blood. The periodic table was barely a whisper. Then the first stars formed. Inside their cores, gravity squeezed hydrogen into helium through nuclear fusion. That fusion released energy the light web now sees. As those stars aged, their cores grew hotter and denser, fusing helium into carbon, carbon into oxygen, oxygen into heavier elements. When the most massive among them died, they did so violently. In supernova explosions powerful enough to briefly rival the brightness of entire galaxies, they forged and flung heavy elements outward: carbon, nitrogen, oxygen, magnesium, silicon, iron, the raw materials of planets, atmospheres, and life. Those explosions did not just add decoration to the cosmos. They transformed it. If Webb is showing us that this process began earlier than we believed, then the universe began chemically enriching itself sooner. That means the first second-generation stars enriched with heavier elements could form earlier. That means rocky planets could theoretically begin assembling earlier. Not Earth, not humans, but the ingredients for complexity were seeded sooner. And that shifts the emotional center of the timeline. Because we tend to imagine the early universe as barren for a long time, waiting patiently before complexity slowly accumulates. Webb suggests complexity wasted no time. Now consider the scale of these first galaxies. Many are compact, far smaller than the Milky Way. Some span only a few thousand light-years across, compared to our galaxy's 100,000 light-year diameter. But within that smaller space, they may pack intense star formation. Imagine a region of space a fraction of our galaxy's size, glowing with thousands or millions of massive stars, each radiating ultraviolet energy into surrounding hydrogen. The radiation from those stars ionizes hydrogen atoms, stripping electrons away. That ionized hydrogen becomes transparent to certain wavelengths of light, allowing more radiation to escape. As more galaxies ignite, they carve expanding bubbles of ionized gas around them. Eventually, these bubbles overlap, and the universe transitions from mostly neutral to mostly ionized. That moment, the end of the Dark Ages, is not a switch flipping everywhere at once. It is more like countless bonfires gradually burning through a fog. Webb is catching some of the earliest bonfires. And there is something else hidden inside the light. Brightness does not only tell us that stars exist, it tells us how many there are and how quickly they are forming. When astronomers analyse these early galaxies, they measure their luminosity, their spectral signatures, their redshift. From that, they estimate star formation rates, how many solar masses of stars are being born each year. Some early candidates imply star formation rates that challenge previous expectations. This is not gentle. This is rapid conversion of gas into stars. Gas collapsing, igniting, exploding, enriching, collapsing again. The universe in its infancy may have been more turbulent than tranquil. And here is the twist. The more efficient early star formation was, the faster galaxies would consume their available gas. Intense radiation and supernova explosions can also blow gas out of small galaxies, temporarily shutting down star formation. So early galaxies may have flickered intense bursts followed by quenching, then reignition as gas reaccumulated. Cosmic breathing. Violent, rhythmic, unstable. This paints a very different emotional image than the one we inherited. Instead of a long, quiet prelude before structure, we see something closer to a cosmic growth spurt. But there is a limit to how far we can see. Even Webb cannot peer back indefinitely. At redshifts beyond about 15 or 20, corresponding to perhaps 200 million years after the Big Bang, the light becomes extraordinarily faint. The first stars themselves, isolated and singular, may remain just beyond our direct detection threshold. We are approaching the boundary. Not the boundary of knowledge, but the boundary of visibility. Beyond that lies a region where the first individual stars flickered alone, not yet gathered into galaxies. Their light may be too faint or too rare for even Webb to isolate directly. But their effects, the enrichment they triggered, the radiation they released echo in the galaxies we do see. And this is where the emotional inversion happens. For decades, the phrase cosmic dark ages carried weight. It implied emptiness, silence, absence. Now that phrase feels unstable. The darkness may have been thinner, shorter, more fragile. Light may have punctured it almost immediately, which forces us to reconsider how we imagine the universe's childhood. Was it lonely? Or was it already crowded with brilliance? And remember, every galaxy Webb finds at these distances is only one among billions. We are sampling tiny patches of sky. If early galaxies are common, then the infant universe may have been densely populated with small, blazing systems. The night sky, if you could have stood somewhere then, would not look like ours. No familiar constellations, no Milky Way band. Instead, perhaps clusters of young galaxies glowing close together, the background still warm with leftover radiation from the Big Bang. It would be alien. And yet, that alien sky is part of our ancestry. Because over billions of years, galaxies merged. Small systems collided and assembled into larger ones. The Milky Way itself grew through mergers, swallowing smaller galaxies, incorporating their stars. Some of the earliest stars that formed in those first galaxies may still exist today. Ancient, metal-poor stars orbiting quietly in galactic halos, relics of cosmic dawn. When we look at Webb's images, we are not just seeing distant objects. We are seeing ancestors. Light from structures that contributed, directly or indirectly, to the galaxy that would eventually cradle our solar system. The Dark Ages were never meant to last. But now we see they may have ended in a blaze so early that the universe barely had time to be dark at all. There is something almost rebellious about it. We built a story of darkness and the universe answered with light. For decades, cosmologists spoke carefully about the first few 100 million years. The equations were clean, the sequence felt orderly, first transparency, then gravitational collapse, then the first stars, then gradual assembly into galaxies. But Webb is revealing something less patient. It is not that the old story was wrong. It is that it may have been understated. To understand why this matters, we have to feel the fragility of those first stars. The early universe had no dust. Dust, tiny grains of carbon and silicates, plays a crucial role in modern star formation. It shields collapsing gas from radiation. It helps cooling processes operate efficiently. It provides surfaces for molecules to form. In the beginning, none of that existed. Gas clouds were exposed. Cooling channels were limited. Radiation from newly formed stars could easily disrupt nearby gas, halting further collapse. So the expectation was moderation, regulation, slow build-up. Yet brightness at extreme redshift implies sustained star formation despite those obstacles, which suggests that either the first stars formed in exceptionally dense pockets where radiation could not easily escape, or the halos that hosted them were more massive and more stable than anticipated. Mass matters. A larger dark matter halo exerts stronger gravity. Stronger gravity can hold onto gas even when radiation tries to blow it away. It can sustain continuous star formation rather than brief flashes. If such halos formed earlier than expected, the entire timeline compresses. And here we brush against something profound. The early universe was not random chaos. It was governed by precise initial conditions, fluctuations in density measured in the cosmic microwave background to 1 part in 100,000. Those tiny ripples became everything. Every galaxy, every star, every planet, every living cell. Webb is showing us what happens when those ripples grow faster than anticipated. But there is another element woven into this. When we look at extreme redshift galaxies, we're also looking at light that has been stretched dramatically by cosmic expansion. Redshift is not just distance, it is a measure of how much the universe has expanded since the light left its source. A redshift of 10 means the universe has expanded by a factor of 11 since that photon was emitted. That is staggering. Imagine drawing a small circle on a balloon. As the balloon inflates, the circle stretches with it. Now imagine that balloon inflating for 13 billion years. That is what happened to the wavelength of those photons. The fact that we can detect them at all is extraordinary. They arrive weakened, diluted across vast distances, their energy diminished by expansion. And yet, their collective glow is strong enough to imply robust stellar populations. That is why some astronomers initially hesitated. Because if these galaxies are truly as massive and luminous as they appear, then they assembled astonishing amounts of mass very quickly. To build 1 billion solar masses of stars in 300 million years requires converting gas into stars at relentless speed. It means that in some regions of the early universe, gravity won decisively. Now shift perspective again. If you compress the history of the universe into a single day, the first galaxies appear just after midnight. The sun forms in the late afternoon. Earth's complex life appears minutes before midnight. Human civilization arises in the last fraction of a second. All of human history fits inside a blink. And yet here we are, detecting photons from that first cosmic minute. There is an almost poetic symmetry in that. The earliest light and the latest observers connected by an unbroken path. But Webb's discoveries are not just about galaxies. They are about boundaries. Before Webb, the observable frontier of galaxy formation hovered around redshift 10 or 11 with tentative detections. Now we're pushing beyond that. Each increment in redshift pushes us closer to the first ignition. There will come a point where galaxies cease to exist in our view, where only isolated stars flicker briefly before fading. We are approaching that horizon, and the fact that we are finding mature-looking galaxies so close to that boundary suggests that structure formation began almost immediately after conditions allowed. It is as if the universe was waiting hydrogen-poised, gravity-ready, and the moment temperature and density crossed a threshold, collapse cascaded. There is also humility embedded in this. Because every time we extend our vision, the universe reminds us that our models are provisional, not fragile, not misguided, but incomplete. And incompleteness is not failure, it is invitation. Webb does not dismantle cosmology, it sharpens it. Already, theorists are adjusting simulations, increasing resolution, testing alternate assumptions about star formation efficiency, feedback strength, and halo growth. The early universe is becoming a more dynamic place in our imagination. More violent, more luminous, less dormant. And that reframes the phrase completely dark. Perhaps it was never completely dark. Perhaps darkness lasted only until gravity could express itself. Because gravity is relentless. Given time, even a little time, it organizes matter into structure. Given structure, fusion ignites. Given fusion, light erupts. And once light exists, darkness is on borrowed time. We are watching the moment darkness began losing. And what makes this even more staggering is that the light Webb captures has been travelling longer than Earth has existed. When those photons began their journey, our solar system was not even dust. They crossed expanding space while galaxies merged. Stars were born and died, planets formed and shattered. They outlived civilizations that would one day interpret them. And now, intercepted, they are rewriting our sense of the beginning. The universe may not have crept into brightness. It may have surged, and we are only beginning to see how fast that surge began. There is a deeper consequence hiding beneath the glow. If galaxies formed earlier, then gravity did not just move fast. It moved with precision, because structure in the universe is not uniform. It follows a pattern, a vast cosmic web, filaments stretching hundreds of millions of light years, intersecting at dense nodes where galaxy clusters reside, with enormous voids in between. That web began as those microscopic fluctuations in the early plasma. If Webb is detecting bright galaxies at extreme redshifts, then those galaxies likely formed at the densest intersections of that web, the peaks of the highest fluctuations. Which means the cosmic web itself began knitting together almost immediately after transparency. Picture an enormous three-dimensional spiderweb made not of silk, but of dark matter. Gas flows along its strands, pooling at the intersections. Those intersections ignite first. Webb is seeing the earliest glowing nodes. And here is where the emotional scale stretches again. The observable universe contains roughly 2 trillion galaxies. 2 trillion. Even if early galaxies were smaller and more numerous, that number hints at how many early ignition points there may have been. Not one dawn, not 10, but countless, across every direction in space, beyond every faint patch, Webb images. The early universe may have been flickering to life almost everywhere gravity found a foothold. And yet we are seeing only a sliver. Each deep field Webb captures covers a region of sky so small that you could block it with a grain of sand held between your fingers at arm's length. Within that tiny patch, thousands of galaxies appear, which means the sky, even in its earliest moments, was never truly empty. It was crowded beyond comprehension, and this challenges something instinctive in us. Darkness feels peaceful, quiet, empty, but cosmic darkness was charged with potential. The moment physics allowed, it detonated into structure. There is another subtle layer in Webb's data that intensifies the story. When astronomers analyze the spectra of these distant galaxies, they look for specific emission lines, fingerprints of elements and ionization states. Hydrogen leaves a distinct signature, so does oxygen, so does carbon. The presence and strength of these lines reveal not just that stars exist, but what kind of stars they are, and how chemically evolved the galaxy has become. Some early observations hint at surprisingly strong oxygen emission in galaxies only a few 100 million years old. Oxygen, which means at least one generation of stars had already formed, fused helium into heavier elements, and exploded. In other words, even at 300 million years, we may not be seeing the first stars. We may be seeing the grandchildren of the first stars. That compresses the timeline even further. First stars form. They live briefly. They explode. They enrich surrounding gas. Second-generation stars form. all within a few 100 million years. That is cosmic adolescence happening almost immediately after birth. Now let's bring this back to us. Our Sun is a third-generation star. It formed from gas enriched by earlier generations of stars that lived and died before it. The heavy elements in Earth's crust. In your bones, in your bloodstream, those elements were forged in ancient stellar furnaces long before our solar system existed. If Webb is showing that enrichment began earlier, then the chemical preconditions for rocky worlds may have emerged earlier across the cosmos. That does not mean life arose early everywhere, but it means the stage was set sooner, and there is something quietly thrilling about that. The universe did not wait billions of years to create complexity. It began almost immediately. There is also a practical frontier embedded here. At extreme redshifts, light from galaxies is not only faint and stretched, it is partially absorbed by intervening neutral hydrogen. Before reionization was complete, neutral hydrogen scattered certain wavelengths, especially in the ultraviolet. By measuring how much light is absorbed at specific wavelengths, astronomers can map how neutral or ionized the universe was at different times. Webb's detections help anchor that timeline. If galaxies are bright and numerous at 300 million years, then reionization may have been underway already. The fog was thinning. The universe was clearing its throat, which means the era we once imagined as prolonged and murky may have been transitional and dynamic. There is a psychological shift here too. We often picture the Big Bang as the most explosive event in cosmic history. And it was in density, in temperature, in scale. But the ignition of the first stars may have been the first time the universe created self-sustaining engines of light. Fusion is different from expansion. Expansion stretches space. Fusion transforms matter. When hydrogen begins fusing into helium inside a star's core, energy is released in a stable, sustained way. Light pours outward for millions of years. That is a new kind of activity, and it began earlier than we thought. There is a quiet elegance to that acceleration. The universe begins in blinding plasma. It cools. It goes dark. And then, almost immediately, it rebuilds brightness from within. Not leftover radiation from the Big Bang. New light, generated by gravity squeezing matter until fusion ignites. That is not random. That is inevitability expressing itself. And the fact that we biological organisms evolved on a planet orbiting a mid-sized star in a spiral galaxy can detect that first ignition is almost absurd. It required centuries of physics, decades of engineering, billions of dollars, thousands of scientists. It required unfolding a segmented mirror in deep space with perfect precision. It required cooling instruments to temperatures colder than Pluto's night side, all to catch photons that left when the universe was still in its infancy. And those photons are telling us something profound. Darkness did not dominate for long. The universe was eager to shine, and we are finally witnessing how quickly it began. There is a moment in every origin story where silence breaks. For the universe, we assumed that moment came slowly. Now it feels more like a rupture. Because if galaxies were already blazing just a few 100 million years after the Big Bang, then the transition from silence to symphony happened with astonishing speed. And speed changes everything. In cosmology, early time is compressed. The first billion years are dense with transformation. Conditions shift rapidly, temperatures fall dramatically, structures emerge. But even inside that compression, we believed there was room for a prolonged quiet phase. Webb is narrowing that quiet. To understand the magnitude of this shift, imagine standing at the edge of a vast, dark ocean. You expect dawn to creep gently across the horizon. Instead, the entire skyline erupts in simultaneous lightning. That is what early galaxy formation may have looked like on a cosmic scale. And the energy involved is staggering. A single massive star, perhaps 100 times the mass of our Sun, can emit millions of times more energy per second than the Sun does, Its ultraviolet radiation ionizes hydrogen across enormous distances. Multiply that by thousands or millions of such stars inside early galaxies, and you begin to sense the violence of that light. This was not warm candlelight. This was radiation capable of reshaping the state of the entire universe. Hydrogen atoms which had quietly existed in neutral form were stripped apart again, electrons torn free, gas heated, transparency restored. Reionization was not decorative. It was transformative. And if it began earlier than expected, then the universe's large-scale transparency returned sooner, which means the cosmos became navigable for light faster. Now consider the geometry of what Webb sees. At extreme redshift, space itself curves our intuition. The galaxies we observe are not where they appear in a simple, static sense. They are at distances so vast that even describing them in miles or kilometers becomes meaningless. Light years help, but even they strain. A galaxy 13.4 billion light-years away is not simply 13.4 billion years distant in space. Because while its light travelled, space expanded. The current proper distance to that galaxy is far larger, over 30 billion light-years. It is receding from us faster than light due to expansion. And yet we can see it. Because we are not seeing where it is. We are seeing where it was. That distinction is not philosophical. It is physical. Webb is a time machine, not in fantasy, but in geometry. And what that time machine reveals is that structure was already substantial at an age when we expected infancy. Some early galaxy candidates appear to have disk-like shapes, not just chaotic starbursts, but organized rotation. That is extraordinary. Rotation requires angular momentum, the inheritance of spin from collapsing gas clouds. It requires stability against gravitational collapse. If confirmed, such structures imply that galaxies were not only forming early, but organizing early. This suggests that cosmic order emerged rapidly from primordial fluctuations. Not chaos resolving slowly, but complexity assembling efficiently. And here we encounter another layer of awe. The initial fluctuations that seeded everything were quantum in origin. Microscopic variations stretched to cosmic scale during inflation. A period of rapid expansion fractions of a second after the Big Bang. Quantum tremors became galactic scaffolding. Webb is witnessing the mature expression of those tremors. Think about that chain. Quantum fluctuations, density ripples, dark matter halos, gas collapse, fusion ignition, galaxies, and eventually, life capable of building telescopes. That entire arc may have begun accelerating sooner than we thought. There is something deeply human about pushing into darkness and finding light. Caves, oceans, space we expect emptiness, and we discover complexity. Webb extends that instinct to the edge of time. For decades, astronomers spoke of the first light almost reverently. It was a boundary, a threshold beyond which lay theoretical reconstruction. Now we are not just reconstructing, we are observing, and the observations are unsettling in the best way, because they suggest the universe may have been more efficient, more decisive, more energetically ambitious in its youth than our models assumed. It did not linger in potential. It acted. There is also humility in how small the sky patch is that delivers these revelations. Webb's deep fields are narrow. They do not sweep the entire cosmos. They peer into a pinprick. And inside that pinprick, entire cosmic histories unfold. Imagine what lies in the rest of the sky. Imagine the billions of early galaxies whose light has not yet been analysed, whose spectra have not yet been passed. We are sampling infancy. And already, the sample is rewriting expectations. But this is not a collapse of cosmology. It is refinement at the frontier. Models evolve, simulations adjust, parameters shift. And the universe remains intact, only more vivid. Because what Webb is revealing is not contradiction. It is intensity. The Dark Ages may have been less an age and more a pause. a breath between plasma and starlight, a narrowing interval before gravity asserted itself fully, and in that narrowing something profound emerges. The universe did not drift toward light. It lunged. It seized the conditions for fusion and ignited, which means that darkness, even at cosmic scale, may never have been dominant, only transitional. And that changes how we feel about beginnings. Beginnings are not always fragile. Sometimes they are explosive. Sometimes they are urgent. Sometimes they are brighter than we ever imagined. And we are watching that brightness arrive, photon by photon, from a time we once called completely dark. There is a threshold in every exploration where the map stops and the imagination used to begin. James Webb is pushing that threshold backward in time. For decades, the phrase "we can't see past this point" carried weight. The early universe beyond redshift 10 felt like mist reachable only through models and indirect measurements. Now that mist is thinning, and what's emerging inside it is not emptiness. It is architecture. To understand why this is so destabilizing, consider how carefully the timeline of cosmic evolution has been assembled. We have the cosmic microwave background, the afterglow of the Big Bang mapped with exquisite precision. We know the universe's age to within tens of millions of years. We know the ratio of normal matter to dark energy. We know how fast space is expanding. From those foundations, we extrapolated forward. First stars around 200 million years. Early galaxies assembling over the next few hundred million. Gradual growth into clusters. That framework still stands. But Webb is crowding the early chapters. If galaxies that appear massive and chemically evolved already exist 300 million years after the Big Bang, then the universe's first act was faster and more productive than we thought. It is like opening a history book expecting cave paintings and finding cities. Now zoom into one of these early galaxies. It is compact, perhaps only a few thousand light years across. Inside it, massive stars burn intensely, flooding their surroundings with ultraviolet radiation. Supernovae detonate. Shock waves ripple through gas clouds, compressing some regions while dispersing others. At its center, a dense region may be collapsing into a black hole seed. That black hole begins feeding. Gas spirals inward, heating to millions of degrees. Radiation erupts from the accretion disk. Jets may punch through the surrounding medium. All of this activity inside a universe not yet 500 million years old. This is not a gentle dawn. This is industrial-scale energy production. And here is something even more staggering. The light we see from these galaxies is not from individual stars. It is integrated light, the combined glow of countless stellar furnaces. That means star formation must have been happening at scale, not isolated flickers. Communities of stars igniting nearly simultaneously. Because brightness at these distances requires numbers. Now imagine how fragile detection is at this edge. Each photon captured by Webb's detectors may have travelled for over 13 billion years. Many are absorbed by dust or scattered by gas before ever reaching us. What survives is faint, stretched, weakened. And yet, even in that faintness, the signal is clear enough to suggest maturity. Some early galaxies show evidence of surprisingly compact but intense star-forming regions. Some even hint at disk-like structures flattened. Rotating systems. Rotation is not trivial. It implies angular momentum conservation during collapse. It implies enough mass and stability to organize motion rather than fragment chaotically. Order emerging early. And then there is the question of abundance. If the first deep fields already reveal multiple candidate galaxies at extreme redshift, what happens when surveys expand, when more regions are observed, when integration times deepen? The census may grow dramatically, which means the early universe might not have been sparsely populated with rare, bright anomalies. It might have been busy, crowded, vibrant. And that reframes how we picture cosmic infancy, not as a long dark hallway before lights flicker on, But as a chamber already filling with brightness as soon as physics allowed, there is something else embedded in this shift, something philosophical without being speculative. We often treat the Big Bang as the most dramatic moment in existence, a singular eruption from which everything followed. But the first stars represent a second ignition. The Big Bang created matter and energy in raw form. The first stars transformed that matter into structured energy release. They were the universe's first sustained engines. They turned gravity into light. And if those engines roared earlier than expected, then the universe's capacity for transformation revealed itself quickly. That matters because transformation is the seed of everything that follows. No heavy elements, no planets. No planets, no chemistry. No chemistry, no biology. No biology, no observers. The speed at which the universe moved from simplicity to structured energy determines how quickly complexity becomes possible. Webb is suggesting that the runway to complexity may have been shorter. That does not guarantee life elsewhere arose early, but it shortens the cosmic prelude. And there is an emotional undertone to that realization. We are not the product of a universe that drifted lazily into structure. We are the product of a universe that surged into it. Now pull back. All of this revelation comes from a telescope parked 1.5 million kilometers from Earth, orbiting the Sun in lockstep with our planet. It sits at a gravitational balance point called L2, shielded from heat, staring outward continuously. Its mirror segments precisely aligned gather ancient light and focus it onto instruments cooled to near absolute zero. That machine is the culmination of centuries of physics, mathematics, engineering, and risk. It unfolded itself in space with no possibility of repair. And it is working. It is working so well that it's pushing us to reconsider the earliest visible chapter of cosmic history. That is the scale of what is happening. Not just new images, not just prettier deep fields, but a compression of the dark ages. A universe that may have wasted almost no time turning on its internal lights. And we're standing here on a small rocky planet orbiting a middle-aged star, intercepting photons from that first ignition. The darkness we thought was complete is revealing itself as temporary. Brief, almost reluctant, because gravity does not wait. And once fusion begins, light is inevitable. The first galaxies were not timid sparks. They were declarations. And their light is only now reaching us. There is a strange intimacy in this discovery. We are not just looking far away. We are looking far back into a time when the universe itself was still deciding what it would become. And it decided quickly. For a long time, cosmologists imagined the first few 100 million years as a gradual climb, small halos merging, gas cooling reluctantly. The first stars flickering alone before galaxies slowly assembled around them. Webb is suggesting that once the threshold was crossed, the climb became a sprint. Because forming a galaxy is not trivial. It requires a deep gravitational well usually dominated by dark matter, large enough to hold gas against radiation pressure and supernova feedback. It requires efficient cooling channels so gas can collapse into dense clumps. It requires a cascade of star formation events, each enriching the environment for the next. And at extreme redshifts, we are seeing evidence that this cascade had already been running for some time, which means something fundamental about early conditions favoured acceleration. The early universe was denser, that matters. Density amplifies gravity. Regions were physically closer together. Gas reservoirs were abundant. There was no prior generation of stars to disrupt structure with accumulated radiation backgrounds. In some sense, the first galaxies formed in a universe that was simpler but more primed. Hydrogen dominated everything. No metals to complicate chemistry. No dust to obscure vision. Just raw fuel and gravity. And when gravity squeezed hard enough, fusion answered. Imagine the first truly luminous region of the cosmos, a dense knot of hydrogen collapsing into massive stars. Each star burns with an intensity our sun cannot approach. Ultraviolet radiation pours outward, ionizing surrounding gas. Supernovae explode within a few million years, forging heavier elements and blasting shockwaves across space. Multiply that by thousands of such regions scattered across the young universe. The result is not darkness pierced occasionally. It is darkness being overwhelmed. Now here is where the timeline tightens even further. If some galaxies at 300 million years already contain heavy elements like oxygen, that means at least one full stellar generation lived and died before that moment. Massive stars live fast 2 to 10 million years. So the first stars may have ignited even earlier, perhaps 200 million years after the Big Bang or sooner. That leaves a remarkably small window between cosmic transparency and cosmic ignition. It suggests that the Dark Ages may have been less an era and more a transition. And transitions can be explosive. There is another layer to consider: luminosity functions. Astronomers don't just count galaxies, they measure how many exist at different brightness levels. That distribution helps determine how efficiently galaxies formed at various times. Webb's early data hints that there may be more bright galaxies at extreme redshift than expected. If confirmed, this implies either that galaxies form stars more efficiently than predicted, or that massive halos were more common than simulation suggested. Neither possibility breaks physics, but both demand refinement, because every model is built on assumptions about how gas behaves under gravity, how radiation feeds back into its environment, and how dark matter clusters at small scales. Webb is testing those assumptions against reality, and reality is leaning toward intensity. Pause for a moment and imagine the human scale again. The Milky Way contains perhaps 100 billion stars. It took billions of years to assemble into its current spiral form. Our solar system formed roughly 9 billion years after the Big Bang late in the cosmic story. All of that feels vast. And yet, compared to the first galaxies, we are latecomers watching childhood photographs. Those early systems may have been smaller, but they were furious in activity. Their stars burned hotter, their radiation was harsher, their environments more chaotic. But from that chaos came enrichment. And from enrichment came the possibility of rocky worlds. Every atom of oxygen you breathe was forged in stellar cores like those early ones or in their descendants. If the first stars formed earlier, then the universe began writing the chemical alphabet sooner. There is something almost poetic in that acceleration. The universe did not linger in simplicity. It moved toward complexity with urgency. Now consider the geometry of observation one more time. When Webb observes a galaxy at redshift 12, the light we detect left when the universe was about 370 million years old. Since then, space has expanded dramatically. The original distance has stretched. Those galaxies are now tens of billions of light years away in proper distance. They are receding faster than light relative to us, not because they are moving through space at that speed, but because space itself is expanding. And yet, their ancient light remains visible because it was emitted when they were closer. We are catching a memory, a fossilized glow from a time when the cosmic web was still knitting itself together. That memory carries information about star formation rates, chemical composition, mass assembly, and radiation fields. And it is rewriting our emotional sense of cosmic dawn. For generations, the phrase there was nothing filled that early chapter. Now we know better. There was gravity gathering. There was gas collapsing. There was fusion igniting. And it all happened faster than we anticipated. Which leads to a subtle but powerful realization. The universe did not struggle to become luminous. It was predisposed to it. Given density fluctuations and the laws of physics, structure was inevitable. Fusion was inevitable. Light was inevitable. The Dark Ages were not a failure of brightness. They were a precondition, a narrowing corridor before ignition, and Webb has stepped into that corridor, revealing that the walls were already glowing at the far end. We are watching the moment the universe learned how to shine on its own. And the shine began sooner than we dared imagine. There is a quiet arrogance in naming an era completely dark. It assumes absence. It assumes stillness. It assumes we understood the tempo of the beginning. James Webb is teaching us something subtler. Darkness was never dominant, only temporary. Because the early universe was not empty space waiting politely for stars. It was a charged arena of gravity, density, motion, and potential energy stretched across expanding space-time. And potential, under the right conditions, does not wait long. Let's step even closer to the edge. At around 100 million years after the Big Bang, the universe had cooled dramatically from its original inferno. Temperatures had dropped to a few dozen degrees above absolute zero. Hydrogen atoms floated through space, tracing the scaffolding of dark matter halos. Inside the densest halos, gravity pulled gas inward. As gas collapsed, it heated. For collapse to continue, it had to cool, in primordial gas. Cooling happens through molecular hydrogen, a fragile molecule, easily destroyed by radiation. That fragility was once thought to slow the first star formation significantly. But what if it didn't? What if dense regions shielded molecules effectively enough to allow rapid collapse? What if turbulence inside halos accelerated fragmentation into multiple massive stars instead of one isolated giant? Then ignition would not be rare. It would be clustered. The first stars may have formed in groups, radiating collectively, amplifying their impact on surrounding space. And once one cluster ignited, its radiation could compress neighbouring regions, triggering further collapse. Light triggering more light. A cascade. Webb's early galaxies may be the fossilised evidence of that cascade already well underway. And here's where the scale becomes almost uncomfortable. When we say 300 million years after the Big Bang, we're talking about a universe still less than 3% of its current age. Imagine a human lifespan of 80 years. That's like witnessing complex civilization at age 2. Not scribbles on cave walls. Cities. Industry. Organization. The implication is not that our understanding was foolish, but that nature may operate at maximum efficiency when conditions align. There is another element that makes this discovery resonate more deeply. Time itself was different. Not in how seconds ticked physics was consistent, but in how dense events were packed. In the early universe, mergers between halos were frequent. Structures collided and combined rapidly. Gas inflows were intense. Starbursts may have been nearly continuous in some regions. It was a high-pressure environment, and high pressure accelerates change. Contrast that with today's universe. Galaxies are farther apart. Dark energy is driving accelerated expansion. Mergers still occur, but less frequently. Star formation rates have declined over billions of years. In fact, the universe's peak star formation period occurred around 3 to 4 billion years after the Big Bang, long after these earliest galaxies. Which means cosmic dawn may have been a preview of that later, grander era. A smaller but intense rehearsal. And here's something even more intriguing. If early galaxies were more numerous or brighter than predicted, they may have played a dominant role in rionization. For years, astronomers debated whether faint dwarf galaxies or rare bright ones were primarily responsible for ionizing the universe. Webb's data hints that brighter systems may have been more common than expected. That changes the balance. It suggests that the clearing of the cosmic fog might have been driven by more powerful, concentrated sources rather than countless faint ones. The first bonfires may have been larger. Now bring yourself back into the frame. Every civilization that ever looked up at the night sky saw stars that were already ancient. The Milky Way's oldest stars are more than 13 billion years old relics of early galaxy formation. Some of those stars may have formed from gas enriched by even earlier stellar generations. When you look at a clear night sky, you're seeing descendants of that first ignition. We are not separate from this story. We are downstream. The oxygen in your lungs may trace back. atom by atom to those first supernovae. The calcium in your bones, the iron in your blood forged in stellar explosions long before Earth existed. If Webb is showing us that those explosions began earlier, then the chain leading to you began earlier. And that realization does something powerful. It shortens the emotional distance between us and the beginning. The Dark Ages were not an unreachable void. They were a brief corridor leading directly to the chemical richness that made life possible. And here is the frontier we are approaching. Even Webb will eventually hit a wall, not because light stops existing, but because the first individual stars may be too faint and too rare to detect directly without gravitational lensing magnifying them. But astronomers are already searching for those magnified first stars, tiny points of extreme redshift amplified by massive galaxy clusters bending space-time. If found, we may witness a single star from cosmic dawn. Not a galaxy. One star. It's light travelling for 13.5 billion years to strike our detectors. That would not just refine our models. It would collapse the distance between origin and observer almost unbearably. But even without that, what Webb has already shown is enough to shift perspective. Darkness was not sovereign. It was transitional. Gravity was already sculpting. Gas was already collapsing. Fusion was already igniting. The universe did not hesitate. It moved from simplicity to structure with urgency. And we are here 13.8 billion years later, catching the echo of that urgency in faint infrared light. The era we once called completely dark is revealing itself as the shortest pause before brilliance. And that brilliance is still arriving. There is a profound shift that happens when darkness is reclassified as delay. For years, the cosmic dark ages carried emotional weight. It felt vast, empty, like a universe waiting in silence before something meaningful occurred. But Webb's discoveries are reframing that silence. It was not emptiness. It was compression. Because when we look at the earliest confirmed galaxies, some now spectroscopically verified at redshifts greater than 10, we are not seeing hesitant beginnings. We are seeing systems that already contain millions, perhaps billions, of stars. That requires not just ignition. It requires repetition. Star after star forming, living briefly, exploding, enriching, triggering the next generation. All inside a few 100 million years. The early universe was not idle. It was iterative. And iteration is the engine of complexity. Think about the physics unfolding inside those first galaxies. Gas falls into dark matter halos. As it compresses, temperature rises. When density and pressure cross a threshold, nuclear fusion ignites. Hydrogen nuclei fuse into helium in stellar cores, releasing energy that pushes outward against gravity. For massive stars, this balance is brief and intense. Inside their cores, temperatures climb to tens of millions of degrees. Fusion proceeds rapidly. Radiation floods outward. Their ultraviolet light ionizes surrounding hydrogen, carving glowing cavities in the primordial fog. Then within a few million years, the core collapses. The explosion that follows can outshine entire galaxies. In that explosion, new elements are forged and hurled into space at thousands of kilometers per second. Those elements mix with surrounding gas, lowering cooling thresholds and accelerating future star formation. This is not a slow burn. It is a feedback loop. And Webb is suggesting that loop was already spinning rapidly when the universe was still in its infancy. Now consider what this means for structure at larger scales. If galaxies were assembling earlier, then galaxy mergers, collisions, and combinations of smaller systems were happening earlier as well. Mergers are transformative. They funnel gas toward galactic centers, triggering starbursts. They feed central black holes. They reshape galactic structure. In a denser early universe, mergers were more frequent. So early galaxies may have grown not only through steady gas accretion, but through repeated collisions. This accelerates mass assembly dramatically. And that helps explain why some early systems appear surprisingly substantial, They may be the survivors of multiple rapid mergers in a universe still less than 500 million years old. Now widen the lens. The cosmic microwave background gives us a snapshot of the universe at 380,000 years old, smooth, uniform, with tiny fluctuations. From that smoothness to organize galaxies in just a few 100 million years is an extraordinary transformation. It is like watching calm water suddenly crystallize into intricate frost patterns across an entire lake. Gravity is the sculptor. Dark matter is the invisible framework. Gas is the clay. Fusion is the fire. And Webb is capturing the moment when sculpture and flame first converge. There is another subtle implication. If early galaxies formed quickly, then the earliest supermassive black holes may have begun growing sooner too. We already know that quasars, luminous black holes with masses of 1 billion suns, existed less than 1 billion years after the Big Bang. Growing something that massive so quickly has always been a challenge. It requires either massive initial seeds or extraordinarily rapid accretion. If galaxy formation began earlier, the seeds of those black holes may have had a head start. The timeline compresses in their favour, which means the universe may have been building its most extreme objects almost immediately after it built its first stars. There is something almost defiant in that, as if complexity is not an accident, but an immediate consequence of physics. Now bring this back to the human scale once more. We often think of ourselves as distant from the beginning, as creatures born billions of years too late to witness the first light. But Webb collapses that distance. It takes photons that left before our planet existed and delivers them into instruments designed by human minds. That is not just technological achievement. It is continuity. The first stars fused hydrogen into helium. That helium eventually became part of future stars. Some of those stars forged carbon and oxygen. Those atoms became part of gas clouds that formed new stars and planets. On one of those planets, chemistry organized into life. That life evolved nervous systems capable of abstraction. Those abstractions led to physics. Physics led to telescopes. Telescopes are now intercepting the first light. The chain is unbroken, which makes the discovery deeply personal. The era we once imagined as entirely dark is not just an academic correction. It is a reminder that the universe was fertile from the beginning. It did not wait billions of years to experiment with complexity. It began almost immediately. And here is the frontier that still beckons. Beyond Webb's current limits lies an even earlier epoch, the formation of the very first stars, perhaps only tens of millions of years after the Big Bang. Their light may be too faint to see directly without cosmic magnification, but their fingerprints linger. In the chemical patterns of ancient stars, in the ionization history of the intergalactic medium, in the structure of the galaxies Webb now observes. We are closing in on the boundary where darkness truly dominated, if only briefly. And the closer we look, the more that darkness shrinks. What was once imagined as a vast empty gulf is revealing itself as a narrow threshold before ignition. The universe did not drift lazily toward light. It accelerated into it. And we are finally seeing just how early that acceleration began. There is something almost unsettling about how little time the universe needed to become recognizable. Not familiar, nothing about those first galaxies would look like the Milky Way arching over a desert night, but recognizable in structure. Gravity pulling matter inward. Gas collapsing. Stars igniting. Light spilling into darkness. The same rules that govern our sun were already operating when the universe was barely a few 100 million years old. That continuity is breathtaking, because it means the laws that shape your morning sunrise were already active near the beginning of time, and they acted fast. Let's feel the compression one more time. From the Big Bang to the release of the cosmic microwave background, 380,000 years. From that release to the formation of the first stars, perhaps 100 to 200 million years. From those first stars to entire galaxies blazing with millions of suns, maybe another 100 million years. That is a blink in cosmic terms. A universe that is 13.8 billion years old moved from plasma to galaxies in less than 500 million years, less than 4% of its current age, and Webb is revealing that this transition may have been even tighter than we thought. When astronomers measure the redshift of these distant galaxies, they are measuring expansion itself, how much space has stretched since the light left. Redshift 13 corresponds to a universe roughly 330 million years old. Redshift 15 would push even closer to 270 million years. Each increment is not just a number. It is a step backward toward ignition, and what we are finding at those steps is not emptiness. It is structure already underway. Now imagine standing somewhere in that early universe not as a human, but as an observer immune to radiation and vacuum. You would not see a black sky scattered with familiar constellations. You would see dense pockets of brilliant blue-white stars clustered tightly, galaxies smaller but intensely luminous. The background glow from the Big Bang would still be warmer than today, faintly humming in microwave wavelengths. Space would feel more compact, galaxies closer, interactions frequent. It would be alien and yet governed by the same physics that governs your heartbeat. That is the bridge Webb is building. From alien infancy to familiar present. There is another implication woven into this discovery that stretches beyond cosmology. If the early universe was efficient at forming galaxies, then the timeline for everything that followed shifts subtly. Chemical enrichment begins earlier. Dust formation begins earlier. Cooling channels become more diverse earlier. That could influence how quickly later generations of galaxies evolved into the complex spiral and elliptical systems we see today. In other words, the architecture of the modern universe may have roots deeper and faster growing than expected. And then there is dark matter, the invisible majority. If halos collapse quickly enough to host luminous galaxies so early, then the small-scale behavior of dark matter becomes even more critical. Is it perfectly cold and collisionless, as the dominant model suggests? Or does it have subtle properties, slight interactions, slight warmth that alter how structures grow at the smallest scales? Webb's observations do not overthrow dark matter theory, but they sharpen the questions. They test the fine print. Because the early universe is the ultimate laboratory, there were no complicated astrophysical processes layered over billions of years. Just gravity, gas, radiation, and expansion. If our understanding of those fundamentals is incomplete, the earliest galaxies will reveal it first. And yet, amid all the equations and refinements, there is a simple emotional truth rising from these images. The universe did not hesitate to create light. It did not remain dark longer than necessary. It transitioned with urgency. There is something almost hopeful in that. Darkness is not permanent. Given structure and time, even a little time light emerges. Now bring this down to the most intimate scale. Every atom in your body was once inside a star. Not metaphorically. Literally. The carbon in your cells was forged in stellar cores. The oxygen you breathe was assembled through nuclear fusion. Those processes began in the first generations of stars. If Webb is showing that those generations began earlier, then the lineage of your atom stretches back even closer to the beginning. You're not just made of star stuff. You're made of early star stuff. And that collapses the sense of distance between you and cosmic dawn. Because the photons Webb captures are not abstract data points. They are evidence of the first engines that eventually made you possible. The universe lit itself. And in lighting itself, it began the long chain that led to awareness. There is still mystery at the edge. We have not yet seen the very first individual star ignite. We have not yet mapped every early galaxy. There may be surprises waiting just beyond Webb's current horizon, perhaps even earlier systems, perhaps unexpected structures. But what is already clear is this. The era we once imagined as completely dark was, at most, a brief interlude. The universe moved swiftly from simplicity to brilliance. And now, 13.8 billion years later, we are catching up to that first blaze. We are intercepting the dawn. not as passive witnesses, but as participants in a chain that began when gravity first tightened its grip on hydrogen. The light arriving now is ancient, but the realization it brings is immediate. Darkness was never the dominant state. It was only the pause before inevitability, and inevitability in this universe shines. There is a final illusion we have to let go of. The illusion that the early universe was primitive. Primitive suggests crude, unfinished, waiting to evolve into something sophisticated. But what Webb is revealing is not primitiveness. It is immediacy. The same equations that govern supernova explosions today governed the first ones. The same gravitational dynamics that shape galaxy clusters now shaped the earliest halos. The same nuclear fusion that powers our sun powered the first stars. The universe did not have to learn how to form galaxies. It already knew. The laws were written into space-time from the beginning. And once temperature and density dropped below critical thresholds, those laws executed without hesitation. That is what we are seeing in these extreme redshift galaxies. Execution. Now stretch the timeline in your mind one last time. 13.8 billion years ago, the Big Bang. 380,000 years later, light is freed from plasma. Perhaps 100 to 200 million years later, the first stars ignite. By 300 to 400 million years, entire galaxies are shining. That means that within roughly the first 3% of cosmic history, the universe had already transitioned from a uniform glow to structured brilliance. Everything else clusters, superclusters, spiral arms, planetary systems, life unfolded within the remaining 97%. The foundational shift happened almost immediately. And this reframes how we feel about beginnings. Beginnings are not necessarily slow. Sometimes they are decisive. There is something deeply powerful about that realization when we place ourselves back into the frame. We evolved on a planet orbiting a star that formed 9 billion years after the Big Bang. Our solar system is middle-aged compared to the cosmos. Our species has existed for barely 300,000 years a blink. And yet in that blink, we built an instrument capable of detecting photons emitted when the universe itself was younger than a toddler in cosmic terms. Those photons travelled uninterrupted for more than 13 billion years. They crossed expanding space as galaxies collided, stars were born and died, black holes fed, planets formed and shattered. They slipped through intergalactic voids stretching millions of light years across. They endured the expansion of space that stretched their wavelengths more than tenfold. And then they encountered a mirror engineered, launched, and unfolded by a species that did not exist when they began their journey. That convergence is almost unbearable in its precision. Light born at cosmic dawn meeting awareness at cosmic dusk. And what that meeting reveals is not fragility. It is inevitability. The universe was predisposed to structure. Dark matter gathered. Gas followed. Fusion ignited. Radiation transformed the state of space itself. The so-called Dark Ages were not an era of inactivity. They were the final inhale before ignition, and Webb has allowed us to witness the exhale. There is still mystery beyond the current horizon. Perhaps even earlier galaxies await confirmation. Perhaps the very first isolated stars will be glimpsed through gravitational lensing, magnified by intervening clusters bending space-time. Perhaps subtle adjustments to our understanding of dark matter or star formation efficiency will refine the picture. But those refinements will not erase the core revelation. The universe did not drift lazily into light. It surged. The darkness was thinner than we imagined. Shorter. More fragile. Gravity needed only a narrow window to assemble the first engines of fusion. And once those engines ignited, the transformation was irreversible. Because light changes everything. Ionized hydrogen clears the fog. Heavy elements seed the future. Radiation sculpts structure. And the cascade continues for billions of years. Right up to us. Right up to this moment where we sit on a small rocky world, orbiting an ordinary star in a spiral galaxy, intercepting the earliest glow and recognizing it. That recognition is the final twist in the story. The first galaxies did not know we would exist. They did not shine for us, but their light arrives anyway. And in catching it, we collapse the distance between origin and observer. The era we once labelled completely dark now feels like a brief threshold, a narrowing corridor between plasma and brilliance. We stepped into that corridor with a telescope, and at the far end, we found light already blazing. The universe began. It cooled. It darkened. And then, almost immediately, it lit itself from within. Not slowly, not timidly, but with urgency. And 13.8 billion years later, that urgency is still arriving photon by photon, reminding us that darkness was never the final word. Light was always waiting. Stand still for a moment and feel the full arc. 13.8 billion years ago, space-time erupted into existence. Energy flooded everything. Matter condensed from that energy. The universe expanded, cooled, and within minutes forged the first atomic nuclei. Hundreds of thousands of years later, electrons paired with those nuclei, and light finally moved freely. Then came the hush. Hydrogen drifting, darkness settling, gravity whispering. We named that hush the Cosmic Dark Ages. We imagined it vast. We imagined it empty. We imagined the universe suspended in waiting. But James Webb has reached back across 13 billion years and placed a golden mirror into that hush, and what it found was not stillness. It found ignition already underway. Galaxies shining when the universe was only a few 100 million years old. Stars burning ferociously inside compact systems. Supernovae already forging oxygen and carbon. Black holes perhaps already feeding at the centres of those first stellar cities. The pause between plasma and starlight was not an era of absence. It was a threshold. And thresholds are brief. Because gravity does not hesitate. Give it slight density differences 1 part in 100,000 and it will amplify them into galaxies. Give hydrogen enough pressure and fusion will ignite. Give fusion enough time and heavy elements will form. Give heavy elements enough space and planets will assemble. The chain is relentless. Webb's discovery does not rewrite physics. It reveals how efficiently physics operates. The early universe did not crawl toward complexity. It accelerated into it. Within 3% of cosmic history, entire galaxies were already luminous. Within a few million years of the first star's ignition, chemical enrichment had begun. Within a few 100 million years, darkness was losing ground across the cosmos. The phrase completely dark now feels fragile. Because darkness, in this universe, is temporary. Light is structural. Think about the photons striking Webb's mirror right now. They began their journey before the Milky Way existed in its current form, before the sun ignited, before Earth cooled, before life emerged, before consciousness wondered where it came from. Those photons left galaxies that may have been among the first ever assembled. They travelled uninterrupted through expanding space stretched, reddened, diluted yet persistent. And now they end in detectors built by a species made from the ashes of earlier stars. That symmetry is not poetic exaggeration. It is physical continuity. The first stars forged the elements. Those elements formed planets. On at least one planet, chemistry organized into biology. Biology evolved into awareness. Awareness built a telescope. The telescope captured the first light. The chain closes. The universe lit itself, and eventually, part of that light learned how to look back. And what it sees is not a timid dawn. It sees urgency. It sees that the conditions for brilliance were embedded from the beginning. The Big Bang did not merely create space and time. It set in motion a cascade towards structure. Dark matter gathered. Gas followed. Fusion ignited. Radiation reshaped the cosmos. Galaxies assembled. Stars recycled matter again and again. Planets formed. Life emerged. Consciousness asked. And now, with Webb's images glowing in infrared hues, we witness the first chapters not as speculation, but as sight. We once thought there was a long, empty corridor at the start of everything. Now we understand it was narrow, almost impatient. The universe did not wait billions of years to become interesting. It was interesting almost immediately, and that realization does something quiet but profound to us. It shrinks the distance between origin and present. It tells us that the story did not drift lazily for eons before becoming relevant. It surged from simplicity to brilliance with astonishing speed. We are not late to a cold universe. We are the continuation of a hot beginning. The early galaxies Webb sees are not just distant objects. They are the ancestors of structure itself, the ancestors of the Milky Way, the ancestors of the Sun, the ancestors of the atoms in your body. When you breathe, when your heart beats, when your neurons fire, you're enacting physics that first blazed into visibility in those ancient systems. The so-called Dark Ages were never permanent. They were the final shadow before ignition. And ignition came fast, faster than we imagined, faster than our models predicted, faster than our intuition was comfortable with. But there it is, light from a time we thought was completely dark. Not faint enough to vanish, not weak enough to miss, strong enough to cross 13 billion years and say, the universe began shining almost immediately. Darkness was only the pause. Light was always the direction. And now, standing at the far edge of time, catching that first blaze in a mirror of gold, we finally understand. The dawn did not creep. It erupted.